In this tutorial, we will be teaching you how to calculate pH and pOH changes during an acid-base titration. So these are the concepts here that we're talking about. Show you how to calculate pH changes during acid-base titration, pOH changes during acid-base titration, and we talk about how curve is derived from an acid-base titration, okay, between a strong acid and a strong base. But before we go into teaching you how to calculate the pH changes in an acid-base titration, we first of all look at how pH changes when a certain volume of a base of known concentration is added to a certain volume of acid of a known concentration. This will provide some background knowledge that you will use when you do your calculations with regard to changes in pH during the titration reaction. So this is the problem here. What will be the final pH and pOH produced by mixing 300 milliliters of 0.1 mole per liter HCl with 200 milliliters of 0.1 mole per liter NaOH? This is how we go about doing that. So we are having a certain volume of HCl of known concentration. We can find the number of moles of HCl in that volume. So the first thing that you do is to find the number of moles of HCl by multiplying its concentration times its volume. So 300 milliliters, same as 0.300 liter, and that is the number of moles of HCl in that volume of acid. Then you want now to find the number of moles of hydrogen ions in the acid. We are doing this because it is the hydrogen ions in the acid that will be neutralized by the OH ions in the base that is added to it. So we want to know what is the original number of moles of hydrogen ions there. Of course, we know the mole ratio of hydrogen ions that is produced for every 1 mole of HCl that ionizes it, and it's a 1-to-1 mole ratio. That is the number of moles of the parent molecule, and you multiply that by the mole ratio there, which is 1-to-1. So we get this number of moles of hydrogen ions in that 300 milliliters of solution. We're pouring into that 200 milliliters of sodium hydroxide solution, this concentration. So now you find the number of moles of sodium hydroxide that is coming in this quantity they bring in here. So that's the volume, that's the concentration, and multiply C times V, we get that for sodium hydroxide. But in there, you want to find one number of moles of that guy there. Do your mole ratio split there, okay, ionization, 1 mole to 1 mole. You take that as a paired compound, and you multiply by the mole ratio, 1-to-1 there, and we get that number of moles of hydroxyl ion. What happens when we mix hydrogen ions with hydroxyl ion? A neutralization reaction happens. So what is going to happen is that every H will be neutralized by 1 OH here. So 1 mole of hydrogen ions will be neutralized by 1 mole of OH ions to form a mole of water. Let's see how many moles of that hydrogen that we had in the previous solution will be used up by that number of OH. So initially, we had that number of moles of hydrogen. Now we're adding that number of moles of OH. So when you do the math here, you'll find that if you minus this from that, you'll end up with this number of hydrogen that's left over. So in the solution, you're going to have an excess of that number of moles of hydrogen ions. 2 important points to note here. There's a change in volume and there's a change in concentration of the acid. So far now, we've only been talking about number of moles of things that came in, and number of moles that have been neutralized, and the number of moles that are left in excess. So now what we need to do, we need to find the concentration of the hydrogen ions that are left in that new volume of solution. Well, we want you to take note of this, that initially we had that number of moles of hydrogen ions in that volume, And now we're adding that number of moles of OH with this volume. Let's suppose we had a bigger container and we pour both of these solutions into it. What will happen is that, like we said before, this 0.02 mole of OH ion will neutralize exactly 0.0200 mole of hydrogen ions, and this new amount of hydrogen ions will be left in excess. But look, that amount is left in a bigger volume, and the bigger volume is the sum of this 200 milliliters and this 300 milliliters here. So these guys are floating around now in 500 milliliters of solution. To find the concentration now, we take that number of moles and divide it by a new volume, which is 0.500 liters. So take the remaining amount of hydrogen ions and divide it by the new volume, and you get this concentration here. That's a new concentration of the hydrogen ions. Now that we know the concentration there, that can lead us to finding its pH. These are the very points we're making here, okay? That figure shows how that number of moles of hydrogen ions are neutralized by exactly that. And these are the leftover ions, number of moles, in this volume here, instead of 300. So go ahead now and find the concentration of this thing, which we did already, in that cylinder here, as equal to this over this, and that's the new concentration. Now that we know the formula for pH, pH is equal to negative log of H plus ion concentration. This is the pH. Calculate the pOH, we know that pOH is equal to pKW minus pH, and this, of course, becomes the pOH. We'll use these strategies to find changes in pH during an acid-base titration reaction. Now, we'll do changes in pH here, right? Watch this now. You want to calculate a change in pH that happens if you have 10 milliliters of 0.1 mole per liter hydrochloric acid when sequentially you add 2 milliliter portions of 0.1 mole per liter of NaOH. So this is what we have here. We are having an initial volume of HCl. This translates into that in liters. It's a monoprotic acid, is strong. So 0.1 mole per liter here, HCl, will give you 0.1 mole per liter of hydrogen ions. So the original pH of this solution here will be equal to negative log of 0.1, which is 1. So pH is equal to 1. And the initial volume is this. So we're saying that because it's a strong acid, we'll assume that the number of moles of hydrochloric acid is equal to the number of moles of hydrogen ions. So what we'll do now, we find the number of moles of H plus ions inside here. N is equal to C times V. So this is equal to C, that's the concentration of the acid, times its volume here. And we end up with that number of moles of hydrogen ions, right? Now you find the number of moles of OH. Here we are seeing again, because it's a strong base, 1 mole of this will ionize to give you 1 mole of that. So the number of moles is found by, again, doing C times V. This is the concentration of the sodium hydroxide that you add in. And this is the volume, 2 milliliters. That's the volume in liters. So you're now adding that number of moles of OH to this number of moles of hydrogen ions. So what's going to happen? This number of moles will neutralize exactly the same number of moles here of hydrogen ions. So what we'll do, we'll take this guy and subtract that from it. Okay? So that's what we'll do. Excess hydrogen will be equal to what you had initially there, which is this, okay? Which is this. And you minus from that amount that you're adding there. And this is what you will be left with. So in this resulting solution now, watch this. You're going to have that amount of hydrogen ions. What happens? Because to that now, you're adding 2 milliliters. The volume here will increase by 2 milliliters. So look, initially you had 10 milliliters, and you're adding 2 milliliters of your sodium hydroxide. So the final volume is equal to 12 milliliters that translate into that, okay? We know the final number of moles of hydrogen that's inside here, which is this. We don't do concentrations equal to N over V. This divided by a new volume here. And this is a new concentration of your hydrogen ions. You do a negative log of that and you get that. Look, the pH went up. What was the pH? pH was 1. Why is the pH going up? The pH is going up because the concentration of your hydrogen ions is getting less because you're neutralizing it by OH ions. Look, this is analogous to what is happening. Let's say I have 4 red balls in that volume of solution, right? And you're adding a blue ball, and every blue ball here is an OH ion, and every red ball here is a hydrogen ion. When you drop that inside there, this blue ball here will neutralize one of the red balls there to form water. So the blue ball and the red ball will disappear. So only thing you'll see are 3 red balls there. But this is bringing in a volume there. It's coming with a volume which is 2 milliliters. So the final volume will be equal to the initial volume there plus this volume that you're adding here. So this is exactly what is happening in this titration here. So here we are now. You added another 2 milliliters. Now that has been added to this here. So that's going to become 14 now. These 2 milliliters of sodium hydroxide will have the same number of moles of OH ions as in the previous case. Thus, we subtract this from what was left inside that solution. What was there initially? Initially, before we add this, that was there in this solution here. We subtract again this from that. So now we're left with a new amount of H in a new volume now. See, that was 12. Now we're adding 2. You end up with 14, which is this. So the new concentration will be equal to Cn over V, which is this one here, plus we end up with a new amount divided by the new volume here. And it gives you this. The negative log of that, again, it's 1.37. Why is it going up? You're taking out more of the H plus and you're adding some more volume.